Welcome again to our video lecture series for GG413 Geological Data Analysis at the University of Hawaii. This video is on section 4.4 of Wessel's notes, One-Way Analysis of Variance, or One-Way ANOVA for short. Now previously we've learned how, if we've sampled two different populations, we've learned how to test whether the means of the populations are different. The application of ANOVA here will be to test between the means among multiple sampled populations. Now, the example I'm going to work from is from Davis's textbook, and he describes 5 rocks of calcite cemented sandstone, and uh, they've been measured for their calcium carbonate content, and each of the 5 samples has associated with it 6 measurements. So the sample size is the same in each case. N is equal to 6. And in this case, we have K equals 5 samples. So what analysis of variance does is it takes all the data that we've collected and identifies different sources of variances among the measurements, and then it quantifies the variance associated with each source. So the objective here is to quantify the variance associated with the different samples, the variance between each sample, and see whether those differences or that variance is large enough to imply that the populations of these samples are different or not. So let's formulate our null hypothesis. And we could simply describe that as the means of calcium carbonate contents for each sampled population. They're all equal to each other. And the alternative hypothesis, so what's the alternative to them all being equal to each other, is that greater than 1 mean, or at least one mean differs from the others. Equivalently, if we describe the mean of population I, mu I, as equal to the mean of the whole of all 5 populations, plus a difference, alpha sub I, and yeah, we have 5 populations. That's funny. I've misnumbered my means in my null hypothesis here. Okay, so that's our first statement of the null hypothesis. Alternatively, if we describe each population having a mean that differs by an amount alpha sub I from the grand mean of all 5 populations, H0, as Wessel describes, can be stated as alpha 1 equals alpha 2 equals alpha 3 equals alpha 4 is equal to alpha 5, and that's equal to 0. And H1 would be that greater than equal, at least 1 alpha is not equal to 0. So how do we do this? Okay, so here's where we're going to apply analysis of variance, where we're going to describe the sum of square total deviations. So we're going to sum over our k samples and over our n measurements of each k samples of each measurement from the grand mean of the whole of all the samples. All right, so xij is the jth measurement of sample I, and x with two bars over it is the grand mean of all measurements. So if we look at our table here, J represents the 1 through 6 replicate measurements of each sample, and I represents the 5 different samples. Now let's break this total sum of square deviations into different pieces. So we have one part in which the mean of sample I differs from the grand mean, and we have one part describing the deviation of each sample from each measurement from its own sample mean. Okay, so I've just basically added the mean of the sample and subtracted it here to show two different parts. And here again, x bar I is the mean of sample I. And we can write that as x bar I is equal to the sum over j of xij over the size of the samples, which in this case is the same for each sample, and it's n, in this case 6. So with a bit of algebra, and you can see page 86 of Wessel's notes, it can be shown that the different cross terms involved with evaluating the sum of this total sum of square deviations can be separated out into their individual sum of square quantities. The first being the sum of square deviations of the means from the grand mean plus the sum of square deviations of each sample value from its own mean. And we can refer to these sum of squares as the sum of squares due to treatment plus the sum of square error. And right. The word treatment actually, well, comes, well, these different quantities have lots of different abbreviations and have a long history. And this term treatment comes from um, agricultural applications, which is where analysis of variance really first started being used heavily. But in this case, our treatment is we're just simply taking different samples. And right, so SSE is our sum of square within the samples. And these would be considered errors if these are basically replicate measurements of the same sample. Okay, so they would be, this would be the variance due to differences between these replicate measurements. Ooh, and I'm noticing I need to correct this last equation. I need a n in front of the first term, and I need to square the argument in the second sums. So please make sure you get these two corrections in your notes. And this first sum corresponds to the sum of squares associated with the treatments, and the second sum, again, is the sum of squares associated with errors. Now let's look at the sum of square quantities visually. Again, the total sum of square variance is due to the sum of square due to treatment plus the sum of square variance within each sample among replicate measurements. So the total variance describes, has to do with the total spread of all these data points, and it's depicted by these long arrows. Again, there are 5 samples shown in these clusters here, and the SSE, the sum of square variance associated or within each sample, describes the spread of the data within each sample. And then the sum of square variance due to treatments, and I'm just now noticing that Davis uses a different term. This is really SSTR. This describes the difference between the means of each sample, or the spread among the means of each sample. So let me give myself a little more room. Put that visual aside here. And so we're going to now create our Anova table, which is a way of organizing these different pieces of information. So the first column of our table is the source of variance. And we have 3 sources of variance. Well, 2 sources that make up the total. The total's down here. And the first source is the variance due to treatments or sampling. And then we have a variance within each sample. And so the columns, so the first column, that's the first column. The second column is the degrees of freedom. The third column is the sum of square. The fourth is the mean sum of square. And then the last is the F values. So the degrees of freedom associated with the number of samples is simply our K samples minus 1 for the grand mean. And in this case, that was equal to 5 minus 1, or 4. The degrees of freedom within each of the within all 5 samples is, so we have K samples, each associated with n minus 1 degrees of freedom, and that in this case gives 25. And the total degrees of freedom are the total number of measurements minus 1. And in this case, we get 29. So you see that for each of these sources, well, the sum of the degrees of freedom with each source equals the total. And that's always going to be the case. So for the sum of square column, we have the sum of square deviations due to treatments, sum of square deviations associated with or within samples, and then we have the total sum of square deviations. We have a mean sum of square associated with the treatments, which is just SSTR divided by the number of degrees of freedom. And that's, let's see, that's referred to as MSTR. MSE is simply SSE divided by the number of degrees of freedom associated with each measurement within each sample. And then the total would be MST. This gives the variance. The total variance. And then for F, we're going to take the ratio of the mean sum of square deviations associated with sampling divided by MSE. Okay, let's talk about how to compute these quantities. So it turns out that the total sum of square deviations is equal to the sum of all the samples, all the measurements that were made. And here I'm going to generalize n, the number of samples, to be allowed to vary between samples. So the sum of all the measured values minus 1 over the total number of measurements times the total sum squared. So here T bar is equal to the sum of all the measurements, and n sub I is equal to the size of the ith sample. In our case, in this example, all the samples have the same size, so they all equal n. And big N is equal to the sum over the k samples of the size of each sample, which in our case, where n is the same, big N is equal to k times n. I'm seeing that I'm forgetting to square each of the sample values. So we can use this is a practical way to compute the total sum of squares. And a practical way to compute the sum of squares between sample means is 1 over ni times the sum of the totals for each sample, t sub I squared, okay, minus what the t bar squared over n. And ti is equal to the sum of all the measurements in the ith sample. And okay, so that's a good way to compute SS, the sum of square due to among the sample means, and then the sum of squares within each sample is simply SST minus SSTR. So when we do that with our data values, okay, here's our data table again. We find that SST is equal to 383.79. SSTR is equal to 237.42. And the difference between those gives SSE, and that's 146.37. And then the means associated with the square deviations between the sample means is equal to 59.35, and MSE is equal to 5.84. Oh, and I'm noticing I need to correct this equation. The number of measurements for sample I should be in the sum. So this is Ti squared divided by Ni, and that ratio is summed for over all k samples. So please make sure you make this correction in your notes. So we've computed these values for our Anova table. Now let's look at F. So F describes the ratio of the variance among sample means over the ratio of the variance of measurements within the samples. Right? Right? It's a fraction between these two sources of variances. So if the variance associated with the sample means is a lot larger than that associated with the measurements within each sample, then that would tend to lead to the conclusion that the means of the sampled populations are different. And if F is small, that is, if the sample means don't vary very much compared to the measurements within each samples, then that would be good supporting evidence that the null hypothesis couldn't be rejected, that there's no reason to reject the possibility that all sample populations are, are equal. So the value we get for F is, let's see, 59.35 over 5.85, and that's equal to 10.14. And so now we're ready to perform our test. We need to see whether this, so this is pretty high, right? Suggesting that the variance associated with variance among the sample means is large compared to the variance within each sample. But let's see if it's statistically significant. So we have to compare that to F, and let's say our significance level is 5%, and we have the number of degrees of freedom in the numerator, which in this case is 4, and the number of degrees of freedom in the denominator, which in this case is 25. Oh, and I'm just realizing that we need to look at the right tail of the F distribution, the far right-hand side, the 95% level of F with the 5% significance level. And so this gives 2.76. So indeed, F is greater than the critical. So we can reject, we need to reject H0 in this case. Right, so we've looked at an example where we have multiple samples with multiple measurements within each sample. We've computed the variances associated or between the means of each sample and separated that from the variances within each sample. And by taking the ratio of those two, we can see whether the variance of the mean was significant or not. And that allowed us to test our null hypothesis. And in this particular case, we found that our null hypothesis should be rejected at the 5% significance level. Before ending, I'd like to just introduce a slightly different problem for which we could apply this one-way ANOVA analysis. And in this situation, there's an engineering laboratory course, and they have a core of sandstone. They have a single core of a sandstone, and the instructor breaks the core into 4 different plugs. And there happen to be 5 students in the class, and each student measures the porosity for each of the 4 plugs. So in this sense, the treatment is between students. So each student makes a sampling, so to speak, of the porosities. And the null hypothesis that the professor had was whether that, each student made equally good porosity measurements. So this is a situation where treatment describes is the right word for describing the sum of squares due to treatment, and that would be equivalent to the sampling of porosity 5 different times. And so to test that null hypothesis, again, the professor would quantify the variance of the mean porosities produced between students and compare that to the variance of the porosities among the 4 cores to see whether the students were all performing adequately well, or to see if one or more students was producing different porosity estimates than the other students. So I'm going to go ahead and wrap up this discussion of one-way ANOVA applied to testing among means of multiple sampled populations.